We're going to talk about 3D sound. We'll talk about the cues that we use as listeners to understand sound in our 3D world. We'll talk about head-related transfer functions, room models, and speaker arrays. We use various cues to sense direction and distance. The interaural time delay, in other words, the difference in the arrival time of sound to the left and right ears, gives us a sense of direction in the horizontal plane. We use spectral cues that we've talked about before due to the pinna, our outer ears, which are asymmetrical with respect to elevation. And so that helps us detect when sound is overhead or in front of us. We use reverberation, and in particular the ratio of direct sound to reverberation sound, as a cue for distance. And we have other spectral cues for amplitude and distance. So computer systems can simulate some of these cues. One of the interesting ideas that has come out of 3D audio research is the head-related transfer function. Here's a reference for more reading. And this all starts with the duplex theory of Lord Rayleigh, which discussed the interaural time difference and interaural level difference. When a sound comes from some angle, we have a difference in time arrival at the two ears, and the head provides some masking or shielding so that the ear that is away from the sound will hear a different level, and actually it's frequency dependent because of different wavelengths of sound. An interesting phenomenon that is predicted by this simple model is what we call the cone of confusion. So everything along this cone will have a similar ILD and ITD. And this is where the outer ear or pinna comes into play. The pinna reflections create interference that's frequency dependent, and so we have basically a different frequency response in our ears depending on the direction of the sound. The head-related transfer function is a way of describing all of these effects, the time delay, level differences, and spectral differences. We measure the effect of the head on the sound arriving at each ear as a function of the source direction, and that's called the HRTF. And then we can apply the HRTF as a filter to simulate placing a sound at some position in space. And there are systems that operate in real time, allow you to virtually move sounds around in space, and they work by interpolating between many different HRTF measurements. Here's what some of these these are head-related impulse responses. Remember that the impulse response characterizes a filter, and here we see the impulse response for different angles in the horizontal plane. So angle is indicated vertically on the vertical axis, and time of the impulse response is on the horizontal axis. And you can see that as the sound changes direction, there are time differences, and there are also some other differences in the impulse response. If we move in the median plane, so this is up and down, you see that the time is more or less the same, but we have some spectral changes indicated out by these variations out here. To use HRTF for actually creating the illusion of things moving in space, typically headphones are used because a headphone can present a different signal to each ear, and we need clearly separated signals to get the most out of head-related transfer functions. The sounds need to change when you move your head. even if the sound source is not moving, if I move my head from side to side, then the model predicts that we need different head-related transfer functions. And so usually this means that you need to do some kind of head tracking and continuously update the HRT apps according to the orientation of the head. Or you have to hold your head very steady to get the effect. Oftentimes, head-related transfer functions are combined with a head-mounted display and used as part of a virtual reality system. Now I'd like to talk about room models. HRT apps are very effective for modeling the location cues of a sound, but they say nothing about reflections. And so in a typical listening environment indoors, there are important reflections off of the walls of a room, which convey both location and information about the room itself that's important for listening. One way to deal with this is ray tracing, where you simulate the path of the sound and simulate reflections off of walls. Unfortunately, audio has very long wavelengths, and so unlike ray tracing in computer graphics, where you think of light as traveling in perfectly straight lines and reflecting or dispersing off of a surface, audio behavior is very frequency dependent because the wavelengths are on the same order of magnitude as the size of the room. But then higher frequencies are much smaller than that. Anyway, we can at least build simple models of reflection based on idealized ray tracing. And the early reflections of sound can do a lot perceptually to convey the room geometry. This is a picture of how to think of doing ray tracing for sound. If we have a room indicated by this square, one cell of this grid, and there's a sound source right here, we can think of this as being a hall of mirrors where we also see a reflected sound source here and another reflected sound source here and so on, all around in this reflected space. So if we draw a line from each of these virtual sources to the listener, that gives us the path length and the angle of that source sound from the virtual or reflected source to the listener. So summing all of these paths together and weighting them by some factors to account for reflection, we can build a simple model. Another thing that we can do to increase realism of sound in a 3D world is to deal with Doppler shift. The idea here is that when a sound is far away, it adds delay to the sound, obviously, and if there's movement, then the change in distance results in a change in delay, and the changing delay causes a frequency shift that we refer to as Doppler shift. So we can simulate Doppler shift using either variable delays or frequency modulation or other techniques. I should point out that when sound is reflected, the Doppler shift can affect reflections in different ways from the direct sound. So this can also result in some very rich effects. Another technique we use for location simulation is panning. We've talked about panning before. Now I'd like to go into a little more detail. Let's imagine doing linear panning where we have a source sound that we want to pan either to the left at speaker location A or to the right at speaker location B. And so what we can do is think about panning as an angle that spans 90 degrees, for example. And we can say that the amplitude to speaker A is 45 minus theta divided by 90, and the amplitude at speaker B is 1 minus the amplitude of speaker A. And so this is called linear panning because as the angle changes from A to B, we linearly change the amplitude from 1 to 0 or from 0 to 1. Now, given linear panning, let's think about what happens at 0 degrees when we are panned into the middle. Well, the power, sound power that is experienced by the listener is the sum of the power at A and B. And what's the power from A? Well, power is amplitude squared. So the amplitude at A is 1/2, amplitude at B is 1/2. If we square those, we get a power of 1/4. And when we sum up the power, 1/4 plus 1/4 equals half. So at 0 degrees, we get half the power that we get when we are panned full left or full right. And this is called the hole in the middle effect. It's something that generally we would like to avoid. And so we can change the manner in which we do panning using what is called constant power panning. And there are a number of ways to achieve constant power. This is a formula from the Curtis Rhodes book. We are using sine and cosine functions, and you notice that because these functions are nonlinear and because they are relatively boosted at the halfway point, that when we take a squared plus b squared at any angle, the power sums up to 1. Let's talk about multi-speaker playback. Stereo is definitely a compromise. It's very common. It was convenient for manufacturers, and so stereo was pushed by the sound industry on consumers. But it's well known, for example, that a 3-channel system with a center channel is, in most cases, superior to stereo. And computer musicians have long been experimenting with more than 2 speakers. Quad arrangements have been very popular. More recently, I would say 8 channels is probably even more popular than 4 right now, and people have built speaker arrays going up into the hundreds. The idea is that if you have enough speakers, you can simulate direction just by routing the sound to the nearest speaker in the direction you want to go, or you can do panning between those speakers. Then to simulate distance, you can use this trick of playing with the ratio of direct sound to reverb sound. And because you want reverberation to be realistically built of many reflections, we often use just one reverberator, and we feed all of the channels with reverberation because reverb is diffuse and non-directional. We can talk about wave field synthesis. The idea of wave field synthesis is to very systematically place speakers and design the sound of the speakers to reproduce the wavefront of imaginary 3D or 2D scenes. This is a photograph from the Technical University of Berlin, which has an operational 832 channel audio system with a 10 centimeter spacing between the smallest speakers. There are larger speakers for lower frequencies that are spaced at 40 centimeters. By computing what sound should emanate from each of 832 channels for each source sound, some very amazing sound fields can be created inside this auditorium. We can move to loudspeaker orchestras, and this is a picture of one example of a system called the Acousmonium, and this is taken in France. With these kinds of systems, usually the idea is not so much to realistically simulate a real sound field, but to use the speakers and the different types of speakers and different speaker characteristics and different elements of the sound to creatively pan and map different voices and musical structures onto this array of speakers. To summarize, we talked about multiple cues for sound location and distance. We talked about the HRTF model, which gives us direction cues but require headphones and head tracking. We talked about using multiple loudspeakers that provide for multiple point sources usually in a plane and using panning as a crude approximation of more ideal perceptual cues. We talked about wave field synthesis that solves many of the problems of spatialization and creating a 3D model, but they're very expensive, requiring up to hundreds of channels of audio to get the effect in a real large auditorium. And finally, we talked about loudspeaker orchestras that, in some sense, accept the speaker as a legitimate sound source and try to capitalize on artistic use of speakers rather than using speakers as a surrogate for a real physical source.